All right, so real quick, we're going to go over lesson 11. It was kind of quick, but this is the one that was what? What in the heck? This is the lesson that was way before your exam. So, what is all this? All right, I guess we're just going over it like this then. So, lesson block 11 covered centroids and distributed loads. And from now on, I think what I'm going to do is I'm just going to put up the picture of the board notes that I wrote. And then, because it's a lot faster than typing it, and then I'll just add things that I missed or things that are important in my discussion of it. But so yeah, here's the exact board notes that I put up in Dr. Liao's class. So basically the idea of a centroid is a description of the center of area. So you guys have heard center of mass, right? That's like the location of the average mass. Centroids are the location of the average area, right? So to find that, you use two moments, right? So you're going to get this table header, like these table headers on your exam, but it's super, super important that you understand what exactly those headers do, if that makes sense. So essentially, you're going to be given some kind of composite shape, which means like you'll have a shape and then either parts will be added onto it or parts will be taken off of it. So you break it up into known shapes. So if you have, the example was this rectangle down here, right? So you had some kind of rectangle with a triangle cut out of one corner and a quarter circle cut out of another corner, right? So essentially what you're going to do is you're going to break it up, list all of the common shapes. So you would list the rectangle, you would list the triangle, and then you would list the quarter circle, right? So just actually list the shapes as they are. And then I would draw a picture of them and then label the dimensions that you know on that drawing. The second column is also fairly easy. It's the area of that shape. So it's a matter of knowing the equations for the area, because I don't believe you're given that on the exam. But they won't give you a super complicated area. So the important thing to know in this column is that if the shape is physically there, it's a positive area, and if it's something that's cut out like this triangle and this quarter circle were, it'll be a negative area. That way, when you sum the areas down at the bottom, you'll have that as your you'll have that in terms of the total area of the shape you were given. So these next four sections are slightly more complicated, but they're super easy if you think about it in the right way. And the reason it took me so long to make this video is because I really, really, really wanted to figure out what exactly the right way to say it was. So these are both moments, right? My and mx are both moments, and then my is the moment about the y-axis, and mx is the moment about the x-axis. So that being said, the formula for a moment is force times perpendicular distance, right? And that's to figure out how much a force causes something to rotate, right? We're wondering how much the area will cause it to rotate. So instead of perpendicular distance times force, it's going to be perpendicular distance times area. But other than that, it's the same thing. So don't be confused by the fanciness of an x tilde, right? Because that figure only represents the perpendicular distance. In the case of my and x tilde, it's the x distance between the centroid of the individual shapes and the y-axis. Because again, you're taking the moment about the y-axis, which means you need the distance between the y-axis and the centroid. So the formulas that you're given on that card that you used in class, you'll get that card on the exam, you'll get it on the quiz, but the formulas you're given are specific to the shape, right? So we'll go over it a little bit in the next slide, but remember that those formulas do not translate to the distance from the axis, it's the distance from a point on the shape. So we'll go over that in the next slide. But the importance of stating that is that when you calculate it based on the card, you're going to get for the, man, I wish I could, maybe I can. So for the purpose of this drawing, right, you're going to get some value of a centroid, say right where my cursor is, but you don't want to measure it from the right angle of the triangle. You want it measured from y. So x tilde is essentially the entire distance of this rectangle, right, minus the distance that you calculated from here to the centroid of the triangle, right? And then down here, because the centroid's already being measured from the center of the circle, it's already being measured from the y-axis, which means you don't have to translate this one. Same with the rectangle. The rectangle is built off of the y-axis, which means that you can technically think of it the same way, the whole shape minus the distance that you calculated for the centroid, but that's only because the centroid of a rectangle is just half the distances in each direction. So I hope that kind of clears that up a little bit in terms of what the tildes mean. I moved that like crazy. In terms of what the tildes mean and how that gets used. And then essentially at the end of this calculation, you just sum up the moments about the y-axis and the moments about the x-axis, and then the location of the centroid. That formula is given. I don't know why I didn't put it on here, but it's the relationship between the moment about the x-axis over the sum of the area, and then the moment about the y-axis over the sum of the area. So that is that. Yes, I covered all that. Okay, going into this a little bit more. There's a couple shapes, and the reason that they chose to do this problem as the practice problem is because those are the most common shapes you'll see, right? So forces will generally be applied in either like a rectangle. So again, the point of learning centroids is that distributed loads, it's basically for the application of distributed loads. That's the only thing you're going to need it for in terms of engineering mechanics. But for distributed loads, they'll either be in a rectangular shape or a triangular shape for the most part. So it's really, really, really important that you know these two. But for centroids problems, you might see this one a lot more often than you think. So in terms of using it in a distributed load, it'll be a rectangle and a triangle for the most part. And in terms of a centroid problem, if you're given one, it'll be it might include this or a semicircle. But so the things that you care about are the area of the shape and then the location of the centroid on that shape, right? So this drawing that I made over here is like fairly similar to the one that is on your sheet. It's just a matter of the triangle that's different. So for a square or a rectangle, the area is just length times width, or base times height, however you want to say it. And then the location of the centroid on the x-axis is just half of this distance. And the centroid location on the y-axis is just half of the height. So it's half the base, half the height. That's your locations. I don't know why it's not written. And then so for the triangle is the one that I don't like how it's written on the equation sheet, right? So this is the one that I would pay a lot of attention to in the video. So the triangle doesn't look like a right triangle on the equation sheet, right? But in terms of a force that you're going to be given, it'll always be a right triangle, because not practically, but in terms of the calculation, it'll almost always be a right triangle, because you're going to have the maximum magnitude of the force applied and then it'll dwindle off, right? So that's why you should probably always consider this scenario as opposed to the one on the equation sheet, right? So the area of a triangle is the same as normal. It's 1/2 base times height, where this is the base and this is the height. The centroid location parts are the parts that are slightly different. I think the equations are the same, but the way that they draw the location is really ugly, especially since it doesn't consider a right angle. So in terms of the location of the centroid on the x-axis, right? That will be measured from the right angle always, and then it'll be 1/3 times the base. So it's essentially this distance. And logically that makes sense, because if it's the average area, it's going to move over towards the side that has a larger area. So this space over here has a much larger area than the space in this corner or the space up here. So essentially the centroid is going to be pulled towards the right angle because that's the fattest part of the triangle. And then similarly, the y component is just 1/3 times the height. The semicircle one, or the quarter circle, I'm sorry, is the exact same as it's written on the equation sheet. I just put it on the board because that was used in that problem. So the only one that I would consider outside of the equation sheet is this scenario here. The formulas are still written on the equation sheet. It's just a matter of knowing that you measure it from the right angle. So all of that was to say that distributed loads are something that we now have to consider. And it kind of makes sense because very rarely in like a real life scenario are forces acting on an infinitely small point. So it's helpful to know this. I mean, in class when you see a force, you still assume that it's acting on an infinitely small point unless it's drawn like this. So this is a distributed load, and that's essentially saying I have this really heavy load, but instead of applying it on just this point, I'm going to apply it across a section of the body so that the body can handle it better, right? But in terms of calculations and in terms of like establishing the reaction forces that supports and stuff like that, you're going to need to assume or like approximate it as one force at one location, right? So essentially distributed loads is, or the lesson for distributed loads is the translation of something like this into one singular force. And then to do that, you need to define the magnitude and the location of the force across that, right? So the magnitude is fairly easy. It's just the magnitude of the distributed load times the area that it's acting over. So your magnitude will essentially be your magnitude given on a distributed load will be newtons per meter or pounds per foot. And to translate that into pounds or newtons, you're going to have to multiply it by the number of meters or by the number of feet. And that'll clear the dimension out of the bottom, out of the denominator. The location is where the shape comes in, or the centroid comes in, right? So in this example, it's a rectangle, right? So you approximate it as a rectangle, and you solve for the centroid at exactly that location, right? So the centroid of this will be right in the middle. You don't necessarily care about the y position of the centroid in a distributed load case because a force has a line of action and the line of action is infinite. So you really only care about the horizontal location or the perpendicular location from the distributed load. So just remember that the magnitude is force times the area, and the location that it's on is at the centroid of the shape that forms the distributed load. And then once you convert it into one force, it'll be essentially an equilibrium problem. You'll be asked to either find an unknown force or find the support reactions or something like that. So for the most part, it's just the only thing different is translating this into a single force. Other than that, I know it's been a weird couple weeks between Labor Day and then the exam. Just wanted to remind everyone my office hours and that I can't help you with the course content if I don't know what you're struggling with, right? And I only get to see only half of you during class. So yes, so please text me, please email me, come to my office hours. I'm here to help. I get paid for it. Might as well make me work for it, right? So other than that, that is all that I have for today. I'm recording the next video right after this, so they'll both be up at one time. So good luck on the quiz and email me with questions.